Hello and welcome to another one of our online lecture videos for differential equations. And today we're going to be taking a look at first order systems, and we're going to start a discussion on the method of elimination. So first we have a theorem, which we'll just talk about briefly, for existence and uniqueness for linear systems. Suppose that the functions p sub 1, 1, p sub 1, 2, so on and so forth, all the way through to p sub n, n, and the functions f sub 1, f sub 2, so on and so forth, all the way to f sub n are continuous on the open interval, capital I, containing the point A. Then given the n numbers, b sub 1, b sub 2, so on and so forth to b sub n, the system x sub 1 prime equals p sub 1 1 t times x sub 1 plus so on and so forth through x sub 2 prime through x sub n prime has a unique solution on the entire interval, capital I, that satisfies the n initial conditions given by x sub 1 at a equals b sub 1, x sub 2 at a equals b sub 2, so on and so forth, x sub n at a equals b sub n. So just talking about the existence and uniqueness for some solution, talking about the systems of first order differential equations. Now we're going to get some practice right away by transforming a differential equation or system into an equivalent system of first order differential equations. And there are some steps involved in doing this that I want to sort of talk a bit about. So first of all, what we'd like to do with our differential equation is we'd like to solve for whatever the highest order appearing derivative is, which is x double prime in this case. So if I solve for x double prime, that means x double prime is equal to, I would add x cubed over, and then I would subtract 4x away. So it looks like this. Now what I would want to do from here is I want to start renaming my variables to sort of give them their own identity. And I want to try to write this, which is a second order differential equation, into a system of first order differential equations. And we're going to be seeing a lot of the same statements throughout. So this first one will serve as sort of a first example for us to look at. The very first statement we're going to make is let x be equal to x sub 1. So we give it its own special unique name. And that means if I differentiate this, that means x prime, or I could call it x sub 1 prime. I'm going to give that the name x sub 2. And since I have to go all the way to x double prime, I want to differentiate again, so that means x double prime, which is the same as x1 double prime, is going to be equal to x sub 2 prime. And I would actually stop here because I want to leave some semblance of a first order differential equation in my work. But now I can go ahead and I can rewrite this differential equation that I started with in terms of first order differential equations. So I would start by making my replacement here. X double prime, I can replace that with x2 prime. So x2 prime equals, and then x cubed, but we said x is x sub 1. So x sub 1 cubed minus 4 times x, but that's x sub 1. But now I need something to connect to this differential equation as well. So then the other statement that we're going to want to work with is that x sub 1 prime is equal to x sub 2. So here, x sub 1 prime equals x sub 2. I'm sort of borrowing from my let statements. And this would be a system of first order differential equations that represents this differential equation I was giving here of order 2. And something worth noting is whatever the order is of the differential equation, that's how many of these statements we should wind up with in our finished answer. So this would be a corresponding system of first order differential equations that can represent this system. A good question might be, why do we care about this? Well, if we're trying to think about solving things, and lots of different ways we could solve a differential equation, but in particular, if I want to solve them very quickly, we could use some techniques from linear algebra, we could use some computer utilities to help us, and it's definitely going to be advantageous in our speed and accuracy of solving these systems if we can reduce them all to sort of a system or a family of first order differential equations. So that will sort of cut through them a lot quicker. So it's good practice to look at, and we'll get an idea as to how this will apply to our elimination method. Let's see another example of this. So again, I'd like to rewrite the system that I have into an equivalent system of first-order differential equations. And I have another one of, order 2. And here notice I have this function of t as well. So regard x as a function of t, even though we didn't really have to think about it too much in the previous example. But my steps that I go through are going to be very similar. So here I want to solve for x double prime, that's the highest order appearing derivative. And that means x double prime is equal to, we have 82 cosine of 4t, and then we're going to have minus 2x prime minus 26x. So that's just resolving this for x double prime. And I want to go through those let statements again. So we'll say, well, let's let x be equal to x sub 1, we'll call it. And then the derivative x prime, you could call it x sub 1 prime. We're going to call that x sub 2. And if I need to differentiate again, that means x double prime is equal to x sub 1 double prime is equal to x sub 2 prime, just differentiating each line. And that's where I want to stop because I only have to go up to x double prime, and since it's supposed to be first order differential equations, I want to leave some semblance of a derivative in there. And now I can go ahead and rewrite this. So we'll say, okay, x double prime, I'm going to replace that with x2 prime, so a first order, and then equals 82 cosine 4t minus 2 times x prime. Now I want to substitute x prime with x sub 2 minus 26 times x, but we're replacing x with x sub 1. But then I'm also going to want another sort of first order piece to this. So next we would say that x sub 1 prime equals x sub 2, and x sub 1 prime equals x sub 2. And this gives me a corresponding first order system that I can work with here. So hopefully not too bad, just a new nomenclature for us, I think. And we'll see one more example of this, and here we're going to bump up the order quite a bit. So here we have the fourth order derivative is the highest appearing derivative. And remember, once we get past the second derivative, that's where we start introducing this new notation using a superscript with parentheses, and inside we have a number indicating the order of the derivative. So that would be the fourth derivative. And if I solve for that, it means I have the fourth order derivative of x is equal to, I got my function of t, which is e to the t sine at 2t. And then I want minus 3x double prime, and then minus x. Now I'm going to have to do a little bit more work to build all the way up to the fourth order derivative, but it's just following that same routine that we saw earlier. So I'm going to start by saying let's let x be equal to x sub 1. The derivative of this, x prime, is x sub 1 prime. I'm going to call that x sub 2. And then differentiating again, x double prime is equal to x sub 1 double prime is equal to x sub 2 prime. But now I'm going to nickname this because I have to continue on from here. I'm going to call this x sub 3 because I got to keep going. And then now I would differentiate again. So my third order derivative is equal to x sub 1's third order derivative, which is x sub 2 double prime, which is x sub 3 prime, and I'm going to give this a special nickname, x sub 4, because I'm still not done differentiating. And then now I can talk about the fourth order derivative, which is where all of this stops. The x's fourth order derivative, well, that's x sub 1's fourth order derivative, which is x sub 2's third order derivative, which is x sub 3 double prime, which is x sub 4 prime. And I'm not going to nickname this anything because this is where I'm actually stopping. So from this, I can build my system of first order differential equations. Let me sort of scroll up a bit here. On this left-hand side, I have to replace x's fourth order derivative. I'm going to replace that with x sub 4 prime. So here we'll start with x sub 4 prime equals, my function of t I just rewrite, e to the t sine it 2t, minus 3 times x double prime. So here x double prime, I gave this the name x sub 3. So minus 3 times x sub 3, and then minus x, where x is x sub 1. But now I have to sort of build to this differential equation with some other first order differential equations. So I want to talk about x sub 4 next. We would say x sub 3 prime is equal to x sub 4. So x sub 3 prime is equal to x sub 4. And I want to talk about x sub 3. Well, x sub 2 prime is equal to x sub 3. I'm trying to do this only with first order differential equations. I want to talk about x sub 2. Well, x sub 1 prime is equal to x sub 2. And that's where I would stop. And remember what we said, the order of the differential equation dictates how many of these pieces we would have in our sort of final answer. Fourth order differential equation, I have these 1, 2, 3, 4 first order differential equations that represent that same system. And like we said, maybe a bit strange at first. I want you to get used to the mechanics of writing it this way. So definitely a new nomenclature for us, something perhaps a bit strange to think about. And this sort of segues nicely into the elimination method. Now for the elimination method, we don't really use x sub 1 and x sub 2, though we certainly can. Instead, we use x and y, and if we needed to introduce new pieces to this, well, we certainly could. And like I mentioned, we could use some nomenclature like x sub 1, x sub 2, so on and so forth. The elimination method, I believe, is fairly straightforward, fairly intuitive, and I think, you have to let me know if it's right or not, I think you're going to enjoy this compared to some of the other things we've seen. So let me know if you're liking the elimination method, but hey, we got to see a first example first. So x prime equals y, and y prime equals negative x is my system, and it's a system of first order differential equations. And in order to work with this, what I want to do is I want to try to get an equation in terms of one unknown and its derivatives. So for example, if I want to get everything in terms of x to start, I could go to this first equation and I can differentiate both sides. And think about the derivative symbolically. Try to keep in mind that x and y are both functions of t. So I'm going to write that above. X and y are both functions of independent variable t. So if I go to this first equation and I differentiate it again, well, I get x double prime equals y prime. Just differentiating, right? X prime becomes x double prime, y becomes y prime. And so now I have this statement I can work with, but I can use that as a substitution in the second equation. So instead of y prime equals negative x, I can replace y prime with x double prime. So x double prime equals negative x. And this is where I can start, right? So now what I can do is I can try to turn this into a homogeneous differential equation, setting it equal to 0. So x double prime plus x equals 0. And now we want to use the characteristic equation with this. So remembering what we said about the characteristic equation, I can replace x double prime with r squared. I would replace x with 1. We sort of skip over x prime, notice that, equals 0. And I want to go ahead and solve this. Looks like if I move this to the other side, I get r squared equals negative 1. And taking the square root means r is plus or minus the square root of negative 1, or r is plus or minus I. And try to remember, the real number is missing. It would be a 0 if I wrote it in. But r is really plus or minus I. You could write that as 0 plus or minus I. And from here, I can start to write out how my solution is going to look. So it's going to be e to the real part times t, so e to the 0t, times, in parentheses, and here, as sort of a general way to write this, instead of using c sub 1 and c sub 2, which you can do, we sometimes like to use capital A and capital B. Does it matter? No, not really. Use whatever unknown you would like for the constant coefficients, but I'm going to do A cosine of, my imaginary part is really a 1 times I, so that's a 1 times t, plus b times sine of 1 times t. But I can clean this up, right? So a lot of things I can clean up here. E to the 0t is e to the 0, which is just 1, so we'll get rid of it. And I can say that this is a cosine t plus b sine t. And this was what we got when we solved working with x, right? We had x double prime plus x equals 0. So this is x at t, x my function of t. So I get the first part to my solution. But something important to notice here is that I'm not done, right? This is actually a system that we're working with involving both x and y. And going back through the statements that I worked with, actually going all the way back to x prime equals y is going to be the easiest to try to get y. So we'll say, okay, that means x prime is equal to y. So if I differentiate this, x prime at t is equal to, if I take the derivative of a cosine t gives me negative a sine of t, and the derivative of b sine of t gives me b cosine at t. Well, this is x prime, but x prime is y, so this is my function y at t. So now I have a general solution for both x at t and y at t. And this would be the solution to the system using that elimination method. And of course, if we had like initial values, we could solve for a and b. I want you to notice additionally that these two aren't without some relationship, right? You'd say, well, your solution for x at t, your solution for y at t, there's some relationship between them. Of course, right? There's this relationship that y is just the derivative of x. So even though I have these two pieces, there is some connection there, some back and forth between them. Let's take a look at another example. And here we do have initial values to work with. So we have x prime equals negative 2y and y prime equals 2x. And so, for example, if I want to try to work with y first, I can do that. If I want to work with x first, I can do that. So for example, if I'd like to, here what I could do is I could solve the second equation for x. So that means I'd have to multiply both sides by 1/2. So we'd say 1/2 y prime is equal to x. And if I differentiate both sides, without really thinking too much about it, 1/2 y double prime is equal to x prime. I can now go into this first equation, and I can substitute x prime. So we'll say, well, how is that going to look? Well, instead of x prime, I can write 1/2 y double prime equals negative 2y. And now what I could do, for example, I could multiply both sides by 2. So y double prime equals negative 4y. And I want to set this equal to 0. I want to work with a homogeneous equation, so I can work with the characteristic equation. So if I add 4y over, y double prime plus, I got to be careful because my 4's sometimes look like y's because my handwriting is not very good. But y double prime plus 4 times y equals 0. And from this, we can go right to the characteristic equation. So here, replacing y double prime with r squared, and then plus 4 times 1, or plus 4, equals 0. Okay, now go ahead and try to solve this for r. So that means r squared equals negative 4, or that r is plus or minus the square root of negative 4, or r is plus or minus the square root of 4 times negative 1. And using that product property of the radical, we get r is plus or minus 2i. And remember, that real part would be a 0 if we want to sort of include that in there. Well, okay, so this puts us sort of well on our path. We can now actually write out the solution for y at t. Since, remember, we worked with y first this time, so this is giving me y. Haven't talked about x yet. We get y at t is e to the 0t times, in parentheses, we have a times cosine of 2t plus b times sine at 2t. And from here, we'd go ahead and say, okay, e to the 0t is e to the 0, which is just 1. So that y at t is just equal to a cosine 2t plus b sine at 2t. And here I have a general solution for y. But I'm not done at this stage. I have to go back and try to solve for x. And there's some relationship between these. What is the relationship? Well, the relationship here is that y prime is equal to 2 times x. Or even better, that I had solved it for x, where x is 1/2 y prime. So that means now that I have y, if I want to find x, I have to differentiate and then divide by 2. So I want to sort of keep that in mind. So x is 1/2 y prime. I'm going to make a little note for myself. X is 1/2 y prime. So I can start by finding y prime at t. Here I need chain rule, right? So the derivative of cosine is negative sine at 2t. But the inside derivative, the derivative of 2t gives me a 2 plus, and then here b comes along, derivative of sine of stuff gives me cosine of stuff, but then the derivative of the inside, the derivative of 2t gives me 2. But now I have to take y prime, and before I get x, I have to divide by 2. So I'll say, okay, what's 1/2 y prime at t? If I divide everything by 2, I get negative a sine 2t. This kind of cleans it up really nicely. And then 2b divided by 2 just gives me b cosine 2t. And this is that long-awaited and anticipated x at t, where x is 1/2 y prime. So definitely some relationship connecting these two general solutions. But now we got both of them. Now we're not going to stop here because we said at the beginning we have these initial values that we can work with. So we have x at 0 equals 1 and y at 0 equals 0. We actually solved for y first, so let me use that initial value first, though the order that you work with them doesn't matter. So y at 0 equals 0. If I go to y and plug in, so here y at 0, we get a times cosine of 2 times 0, that's cosine of 0, which is 1, plus b times sine at 0 is 0. So this just gives me a times 1 just gives me a, and we said y at 0 is equal to 0, so there I get a is equal to 0. Well, we're almost running out of space too, got to be careful, I guess. So y at 0 equals 0, and then we work with x at 0 equals 1. So if I plug 0 into x, which is here in the pink, x at 0, remember sine at 0 is 0, so that's gone. Cosine at 0 is 1, so that's going to give me b. And we said x at 0 equals 1, so we get b equals 1. Right, x at 0 equals 1. So now that I know what a and b are, I can go ahead and write out my particular solution. Let me write x first, just because now that we have all the pieces, it feels like it would be, rude to the alphabet to not write x first. I don't know. X at t. Now, lucky for me, because I'm running short on space, a is 0. If a is 0, this entire first term is going to get killed off, and I'm left with this b cosine 2t, but since b is 1, that's 1 cosine 2t, or just cosine 2t. And for y at t, remember a is 0, so that entire first term gets killed off, and b is just 1, so that's sine at 2t. So we work with those initial values to now move away from our general solution into a particular solution to our system. So working with those initial values there. And let's take a look at one last example of this elimination method. We are going to take a look at it again in the next lecture as well. So we'll do a continued on this elimination method where we start to talk about introducing more into it. But I think for now this is a good first step into these first order systems and a bit of the elimination method. So here again we have initial value problem. We have a system x prime equals negative y and y prime equals 13x plus 4y. And I want to try to work with this. I want to try to see what I can do in this case. What I could do is I could work with this equation here on the left. I could solve it for y, I think would be good. So here if I multiply both sides by a -1, I get that y is equal to negative x prime. Just a small rearrangement of this. And if I want to talk about y prime, I just differentiate both sides. Keeping in mind that x and y are functions of t, I can just differentiate in an abstract way, saying that then y prime is equal to negative x double prime. And I can substitute now into this second equation. I'm going to try to get everything in terms of x, it looks like. So y prime on the left, I can replace that with a negative x double prime equals 13x plus 4 times y, but y is negative x prime. And I do want to turn this into a homogeneous differential equation, so I want to get everything on one side. I want that first, that highest order term, to actually have a positive coefficient. Why? I don't know, it's just a preference. Hopefully you prefer that too, but if not, then it's nothing really worth arguing about, to be honest. I'm just gonna, if it helps, then it's less movement as well. So I don't know, a lot of good reasons, right? If I move that term over, it's gonna be positive x double prime. I'm gonna write x prime next, which is a negative 4x prime, and it stays on that side. And the 13x is already there as well. And now this is equal to 0. So I think it looks good. This looks like the appropriate homogeneous differential equation I would want to work with. And from here we can work with our characteristic equation. We'll sort of jump over here. That's going to be r squared minus 4r plus 13 equals 0. I don't know, 13 is, prime. It doesn't look like this is going to factor quickly. So I would want to work with the quadratic formula. And we have b is negative 4, so negative b is positive 4, plus or minus the square root of, I want negative 4 squared, so b squared. Think of negative 4 squared like being 4 times 4. It is 16, but let me write it like this. And then minus 4 times a times c, so that's 4 times 1 times 13. And then all divided by 2 times 1. And maybe it's weird that I didn't write negative 4 squared, or I didn't write 16. I actually chose to write it as a positive 4 times positive 4, which is the same. It's just kind of strange that I wrote it that way. The reason why I did this, it's going to help me do some of the work by hand. I don't like multiplying numbers any more than the next person. So what I can actually do is I can factor a 4 out, and I'm left with this 4 that I left behind, minus, I'm left with 1 times 13, which is 13. And then all over 2 times 1. And this just makes it a little bit more manageable to do by hand. So we got 4 plus or minus the square root of, and here we have 4 times, now 4 minus 13 is going to give me negative 9, so I can't avoid all the arithmetic, but most of it. And 2 times 1 is 2. And then here I could think about my product property of the radical. Here I could say 4 plus or minus, this is going to be radical 4 times 9 times negative 1 all over 2. And split up that square root and reduce where we can. So we'll say 4 plus or minus 2 times 3 times I all over 2. And this is really a 4 plus or minus 6i all over 2. But I'm just going to reduce anyways, so maybe it doesn't hurt to even leave it like this at this step and just do the next move, which is 4 divided by 2 gives me 2, plus or minus, here the 2's cancel, so I get 3i. And so now that I'm done working with the characteristic equation, I can return back to what I was doing. What was I doing? I was trying to get a solution here for x, a function of t. And my characteristic equation is going to tell me what that looks like. X, my function of t, is going to be e to the 2t times in parentheses a cosine of 3t plus b sine of 3t. And so that looks really good right away. Next, what I want to do is I want to try to find y. Well, what is y? Y is negative x prime. So I'm going to make a note for myself so I don't have to keep traveling back up here. Y is equal to negative x prime. So the first thing I'm going to have to do is differentiate, right? I want to find x prime. So here, x prime at t. And this is going to mean product rule with chain rule all over the place. So I'm going to rewrite e to the 2t. Derivative of a cosine 3t with chain rule is going to give me negative 3a sine of 3t plus derivative of b sine of 3t. I'm going to get b comes along, I get cosine of 3t, inner derivative gives me a 3, and then I want to add to this. Now I'm going to rewrite this second factor here, so I'm just rewriting a cosine 3t plus b sine of 3t times the derivative of e to the 2t, which is e to the 2t times 2, and that's with chain rule. Now, I want to try to collect this a little bit better. So before introducing, so I say some minus sign, what I'm going to do is I'm going to factor e to the 2t all the way out. And what am I left with? I have a negative 3a sine 3t plus I have 3b cosine 3t. I factored the e to the 2t out, but I do want to bring this 2 in. So we'll say plus 2a cosine 3t, and then plus 2b sine 3t. That looks pretty nice, I think. Now, to get y at t, all I have to do is make this negative, and there's a lot of stuff here. I don't really want to rewrite everything, so let me make it negative by just putting a minus sign right in front of it deliberately. And then, if you believe me that negative x prime is y, I can just go here. And we have y at t. All this stuff. So this is my general solution for y at t. I had to differentiate my general solution for x at t and flip its sign. I didn't circle that one either, so let me circle them both. Now, we have initial values, right? So who am I kidding with circling these? We're not quite done. The initial values that we have, x at 0 equals 0, y at 0 equals 3. X at 0 equals 0, y at 0 equals 3. And now we can move away from the general solution to the particular solution. In some cases, and I'll just mention this because this is our last example, in some cases, if you work with the initial values earlier on, let's say if I worked with the initial value first before trying to find y, it might cut down on some of the workload. But I want you to think about the disadvantage of doing that is that now I don't have a general solution in full description for y at t. So although it does maybe sometimes, not all the time, sometimes it does make the work a little bit faster for the particular solution, it omits getting a nice general solution for both pieces, which maybe you don't care about as much as I do, but I have a feeling that you care about it too. So let's work with our initial value here for x. X at 0, so I want to plug 0 in. And what do we get? We get e to the 2 times 0, which is e to the 0. And then in the parentheses, we get a times cosine at 0, which is a times 1, plus b times sine at 0. And sine at 0 is just 0. So we can clean this up. E to the 0 is 1. And then a times 1 is a, and then b times 0 is 0. So all that we get is a, and a is equal to 0. So that's giving me the value for my first unknown coefficient. Now I want to work with this other initial value, y at 0 equals 3. So I'll say, okay, y at 0, if I plug 0 into y, and there's a lot more terms in the general solution here, I get negative e to the 0, which is negative 1, times in parentheses, Now remember, sine at 0 is 0. So here I get 0. Cosine at 0 is 1. So I get 0 plus 3b times 1. Plus 2a times 1. I'll flip up in a second, but that last term is going to be a 0 because it had a sine in it, right? So this is sine at 0 is 0, 2b times 0 is 0. So what do I get from all of this? Well, I have negative, in parentheses, 3b plus 2a. What do I know? I know that a is 0. So if a is 0, then that second term is gone. So I just have negative 3b. And we said y at 0 is equal to 3 was the initial value. So negative 3b equals 3. If I divide both sides by negative 3, that means b is equal to negative 1. And now, including this information, I can go and write those particular solutions. So a is 0, it's gone, forget about it, get over it. And b is negative 1, which isn't so bad. So here for x at t, I have e to the 2t. Let me write this down, x at t. It's e to the 2t. And that first term had an a, which is a 0, right? And then here we have plus negative 1 times sine at 3t. I'll clean that up in just a moment, but let's look at y at t next. Y at t has this negative e to the 2t in front. So let me write that down first. It's a minus sign. I don't know if I made it look more convincingly like a minus sign, but it definitely stands out more now. A is 0, so that first term is 0. B is negative 1, so we get negative 3 cosine 3t. A is 0, so 0 next, and then here we get a negative 2 sine 3t. Yeah, negative 2 sine 3t, perfect. And now I can clean these up because I got some stuff here that I don't really need, and I can probably write it in a little bit nicer of a way. I also like to switch colors a lot, so let me do that. X at t is just e to the 2t times negative sine 3t. It looks a little bit prettier if I bring that minus sign in front, subjectively. Negative e to the 2t times sine at 3t, bam. And y at t, I have this minus e to the 2t, and then negative 3 cosine 3t, negative 2 sine 3t. Bring that minus sign in. I should resolve just to give me e to the 2t times, in parentheses, 3 cosine 3t plus 2 sine 3t. And this looks great. So here we have our particular solutions on x at t and y at t. And that's it for the section. Let me go ahead and put the homework in the homework jar. Please take a look at the homework that we have on our online platform. We are going to talk about the elimination method again in the next upcoming video. So I hope you enjoyed it. We're going to talk a little bit more about it, and then we'll move on to some new topics beyond that. But otherwise, thank you so much for spending the time with me. No matter what, remember to keep learning, keep dreaming, and to follow your heart. And I'll see you next time.